Thank you, Edward, for this very exciting talk. I'm making comments on cosmic microwave background to what we measure and what we see in AVM collisions. So I have a question. In one of your slides, you showed the cosmic microwave background temperature fluctuation 10 to the minus 5. And in the same slide, you show the temperature fluctuations delta T by T, early stage fluctuation of 10 to the minus 1.
Wait a second. You speak about this turbulent cascade, right?
You don't have a slide number, so I didn't note down the slide. Delta T by T. Delta T by T.
Delta T by T.
Yeah. I think it's before. Yeah, it's not about gravity, it's delta T by T. Yeah, listen, this is the one. So you have 10 to the minus 5 from CMB. And how did you get this number 10 to the minus 2? And you say it's initial state fluctuation. I think initial state fluctuations are much larger.
Yeah, they are much larger and then they are kind of, yeah, okay. They are locally large, so you're asking if what happened at every time. So people who start Hydra either started very early, and they start from color glass or other members, and they got through them. Then they're bumping, they're very bumpy, and if you calculate, there are many bumps. There's as many, not as many as nucleons, but as many as quarks. There are hundreds of them, yes, of these bumps, and their amplitude is large. And if you calculate harmonics, you get harmonics constant all the way up to about n equal 100. So, you calculate. What happened, and they're large. Then Hydra cores start drinking, and what happened is that out of this 100 harmonics, 99 or 90, I should say, died immediately because the viscosity killed them, because this exponent of minus x squared killed them. And after that, only lowest harmonics remain. So when I say on the order of percent, I mean if you calculate finally coefficient epsilon 2 or epsilon 3 or epsilon 4 of the magnitude of second, third, fourth harmonic, they are several percent. Okay. And they basically remain like this. Also, what is important for this theory is as soon as it is smaller than 1, significantly smaller than 1, you linearize it here. You have a smooth Hydra plus a wave. Whether a wave is 10%, 1%, and minus 5, doesn't matter, it's a linear equation. The amplitude goes away, and you just solve this linear equation. So all these phenomena do not depend on amplitude. Of course, what you measure depends on amplitude. So when I, for example, show these horns, it's very much exaggerated. So if you see particle distribution, you have here 17.5, and these horns are, this magnitude of this is small compared to overall magnitude. So this is the effect of percents, these are these bonds. Because this is also clear, because for each wave, probability that two particles come from this phenomenon for one circle is small. You need two particles which are both of this phenomenon. There are many other circles on it, coming from many other bonds, but they are incoherent to each other. In the linear approximation, they don't notice each other. So, when I said they're small, I mean in the resultants. But of course, we have our beautiful experiments which have on the take 1 billion events, and each event has hundreds, thousands of particles. So it is enough statistics to go all the way, not only to 7 harmonics, but all the way to 9, as I have shown. And the total amount of information we have in collisions is about as large as the total amount of information about the universe with cosmic matter in the ground. They have big sky, but only one event, as I said. And we have billions of events.
Okay, so
Can I ask you a question?
Yeah, sure.
Yes, sure. About the option we should use while we apply micro small system. But it is that for one thing another system that there is one thing to solve. So
There is one, I didn't hear you very well.
I mean, you have said that we are cautious about the use of micro small system. Because often you see that the small systems are usually like we did. So how cautious should we apply micro small system?
Well, of course, it's natural question. The question is whether the predicted phenomenon exists or not. So if you take a system too small, namely if you take ordinary PT collision, we know none of this phenomena exists. So it only appears at certain size of the
There is counter argument that once you or one can understand that this is kind of an extreme and then this is area at the same time.
Yeah, so when we go, for example, to PP at high multiplicity, like 100 per, in the notation of the experiment, high multiplicity PP, and compare it to let. The system is smaller. It is several times smaller radius, from say 6 kilometers or whatever. On the other hand, the density is significantly higher. The density is much higher because you see how much entropy from this one. Now, if you go to quark-gluon plasma and look at its property, quark-gluon plasma is practically conformal. If you are somewhat away from phase transition region, it becomes conformal. In other words, plasma made of massless photons, massless gluons and quarks have no scale of their own. And if you make a fireball smaller, but at the same time denser, the plasma doesn't really care. It has small fireball and large fireball. If plasma don't have a scale, it doesn't care what the fireball is. This is what I'm saying is approximate. Of course, the density go up, but not that much. Yet we do see, if you compare radial flow magnitude in the small systems and lab, we see that small systems even outperformed, that they have larger, more robust explosion, which is counterintuitive, but yeah, the system is smaller, but it becomes more macroscopic. Why it becomes more macroscopic? Because there is more stuff in it. So the microscale is smaller as well. And the ratio, Hydra only cares in other language about ratio of macroscale size of the fireball to microscale temperature. And that is not so obvious whether it is the same, larger, or smaller. It depends on multiplicity.
okay, so you have another question? Okay, so we thank Mr. Shurya for his wonderful presentation. And Vikash is not here right at this moment. He has gone somewhere. So thank you. And we end today's session. Thank you very much.
Okay.